Carbonyl groups occur when you have a carbon that has a double bonded oxygen. Now, because you have polar CO bonds, this makes your molecule polar overall. Because I have slight charges and there's no H directly attached to the oxygen, then I can take two organic compounds with carbonyl functional groups and attract them using a dipole-dipole attraction. This increases the melting point and it increases the hardness of the compound. When I try to dissolve a chemical with a carbonyl group on it in water, because I have an O with lone pairs, it can accept one hydrogen bond from water. This increases the solubility of the compound. A carboxyl functional group is a combination of two of the previous ones we've learned. You have a carbon that has a double bonded O, so a carbonyl, and on that same carbon you have a hydroxyl functional group. Because you have polar CO bonds and polar OH bonds, you get an overall polar molecule. Now, if you have a look, we have two different intermolecular forces we can make. On the CO bond, because there's no H directly attached, we can make dipole-dipole forces just like a carbonyl. But because we have an H directly attached on this hydroxyl, we can also make a hydrogen bond. This drastically increases the melting point of the compound and the hardness. When I try to dissolve a carboxyl functional group in water, again, I can make two different forces. On the OH part of the carboxyl functional group, I can make a hydrogen bond. But because there's no H directly attached on the double bonded O, I can accept one here, which is still a pretty strong attraction. This again drastically increases the solubility of the compound. An ester functional group combines an alkoxy and one of the carbons also has a carbonyl group attached. Because you have polar CO bonds, you end up with an overall polar compound. Because there are no H's directly attached to the O's in an ester, you can only dipole-dipole, but you have two oxygens, so you have two possible locations to do that. This increases the melting point and increases the hardness of the compound. Again, because there's no H's attached to the O's, an ester cannot make hydrogen bonds, but they do have the lone pairs necessary to complete and accept two hydrogen bonds from water. This increases the solubility of the compound. The last functional group is known as an amide. It's a combination of an amine and a carbonyl group. There are 3 different varieties. You can have a primary amide where your nitrogen is attached to one carbon that also has a double bonded O. In a secondary amide, your nitrogen is attached to 2 carbons. And a tertiary amide, your nitrogen is attached to 3 carbons. Each of these nitrogens has a lone pair, giving it a trigonal pyramidal shape. Because you have polar CO bonds, and polar CN bonds, and polar NH bonds, each classification of amine is a polar compound. There's a wide range in melting points and hardnesses for amides, depending on which classification you have. Because a primary amide has 2 H's attached to the nitrogen and an oxygen, it can make 2 hydrogen bonds with another amide and form one dipole-dipole attraction. A secondary amide can make 1 hydrogen bond and 1 dipole-dipole, and a tertiary amide, because there is no H's directly attached to the O or the N, can only dipole-dipole twice. All of these forces increase the melting point and the hardness of the compound. The same variation exists in the solubility of amides. Because there are 2 hydrogens attached to the nitrogen, a primary amide can make 2 and accept 1 hydrogen bond from water on the C double bonded O. A secondary amide can make 1 and accept 1, whereas a tertiary amide can accept 2 hydrogen bonds from water. All of these increase the solubility. At the bottom of the note, you have 2 boxes. This one summarizes the difference between making hydrogen bonds and accepting hydrogen bonds. And the other box describes how the size of your organic molecule influences its properties. If 2 molecules have the same functional groups but different sizes, the following effects occur. The larger molecule will have stronger London dispersion forces. Therefore, it will have a higher melting point. However, the larger molecule will be less polar overall. If you think about having a really long alkane with a hydroxyl functional group at the end, this part of the molecule will be non-polar. This part will be polar. The larger the non-polar area, the more that polar hydroxyl group will get spread around the molecule and the less effect it will have. Therefore, larger molecules will be less soluble in water because they are less polar overall.